Okay, we're going to be working in Python again today, and our task is to take our simple inverted pendulum model here with its 1 degree of freedom and convert it to this 5 degree of freedom model you see here. This model is going to have 3 segments instead of 1. It's going to have a trunk, a thigh, and a shank, and it's going to have a total of 5 degrees of freedom. And what are those degrees of freedom? Well, there's 3 rotational degrees of freedom. There's the angle of the trunk relative to the room. There's the angle of the thigh relative to the trunk, that's the hip angle. And there's the angle of the shank relative to the thigh, that's the knee angle. Those are 3 degrees of freedom. What about the other 2? We're also going to disconnect the foot from the ground here so that the whole model can freely translate up and down and left and right. And so that gives us our total of 5 degrees of freedom, those 2 translations and those 3 rotations. Those 2 translations are specifically going to be the horizontal and vertical position of the hip in the global frame there. So horizontal and vertical hip position, angle of the trunk, angle of the hip, angle of the knee, for a total of 5 degrees of freedom. Now, how do we define that model? Let's start from our simple model here in PyDy, in our Python code for the 1 degree of freedom inverted pendulum model. So if I go and run this model, just to remind you what we're starting with here. That should spit out my equation of motion for my inverted pendulum, which was this equation of motion here. Now let's start from here and expand this to that 5 degree of freedom model. So this should give you a sense for how you can start from a simple model in PyDy and expand it to a more complicated model. Let's rename this file before I overwrite the old one accidentally. And we're going to have 3 segments with 5 degrees of freedom. And so I need parameters here for the inertial properties of my additional segments. So let's add those. And I need my additional reference frames for my new bodies B and C. Body A is going to be my trunk, body B my thigh, and body C my shank. I now have 5 degrees of freedom instead of just 1, and 5 generalized speeds to go along with those. I've got 2 joints, the hip and the knee, and each of those is going to have a torque applied to it, tau 1 at the hip and tau 2 at the knee. I'm also, remember, going to have a contact force on the foot or on the ankle at the end of the shank here. That's going to be a 2D contact force, so we'll call it Fx1 and Fy1. And I added the 1 there because we're going to eventually add a second contact force on a different part of the model, but for now we'll just have this 1 at the foot, this foot ground contact force, with a vertical component Y and a horizontal component X. Still got my global reference. I need a center of mass for each of my new segments. And I'm going to have 2 additional points of interest here. And I'm actually going to change my labels here. I'm going to call point 2 the hip, and point 3 the knee. Let's orient my bodies here. Q1 and Q2 are going to be my translations, so Q3 is going to be my first rotation. That's my trunk angle, or my angle relating body A to global frame N. I'll have a similar thing for Q4. That's my angle between body B and body A, my hip angle. And then similar thing for Q5, that's my angle between bodies C and B, and that is my knee angle. Okay, then let's define my point of interest. Point 2 here is going to be my hip, and it's no longer fixed at 0 in the global frame. It is a translation Q1 along the global x-axis plus a translation Q2 along the global y-axis. And that's going to be my hip position. P1 here is still going to be the top of the head. So starting from the hip and doing a translation all the way along the long axis of the trunk segment. And P3 is also going to start from the hip and do a translation in the negative direction all the way along the thigh segment. That'll give me my knee. And then P4 starting from the knee all the way to the end, giving me the ankle. Okay, and then the center of mass locations for each of my bodies here. It's my trunk COM from the hip, my thigh COM from the knee, and my shank COM from the ankle. Okay, I now have 5 kinematic constraints defining my generalized speeds. 2, 3, 4, 5. And I have the 3 angular velocities defining V3, V4, and V5. Okay, the most complicated part of expanding the model here, sorry, this should be a B, not a C. The most complicated part of expanding the model here is defining these linear velocities. And so let's just start from scratch there. Remember, for Kaynes' method, we need to define a velocity vector for any point that has an inertial force acting on it. So that for us is going to be the center of masses. And any point that has an active force acting on it. So that for us is going to be the foot where that ground reaction force is acting, and the joints where those moments are acting. So we need to define the velocity here for all of our joints and for all of our centers of mass. Okay, I'm first going to set the velocity of my global frame origin to be 0. Oops. And then in that frame, I'm going to set the velocity of my hip, which is just the time derivative of the position of the hip from above. And remember here, this is the linear velocity of the hip, the translational velocity of the hip in the global frame. It's not the angular velocity of the hip. Okay, with those 2 points having their velocities defined, the rest of these definitions will use that v2-point theory command, where this is the theory from mechanics, where if I know the velocity of some point on a frame, and I have the angular velocity of that frame defined, which I just did up here for all my frames, then from that information I can compute the velocity of any other point on that frame. So for this V2-point theory here, if I want the velocity of the center of mass of the trunk, I have to tell it the velocity of some other point on the trunk that I already know. The hip is on the trunk, so I know that. And then I have to tell it the reference frame that I want all this expressed in. Let's just use the global frame. And then I have to tell it the body that this point exists on, which has its angular velocity already defined, and that's frame A here. So this is my trunk COM velocity. Okay, I can do similar thing to define the velocity of the top of the head. That also is on the trunk, so it looks similar there. And similar thing here for the center of mass of the thigh, because the hip point 2 here also exists on the thigh, frame B. And similar deal here for the rest of the points of interest in my model. Oops. Okay, let's review here. When I'm defining these linear velocity vectors, I need to define them for any point of interest, which is basically any point where an active force or an inertial force is applied in the model. So that's going to be my center of masses, and anywhere else where an active force is applied. In this case, it's the ankle, and the where the ground reaction force is, and the knee and the hip, where those moments are. Okay? For the points beyond my initial 2 points here, the global frame, and then kind of my frame or my point just defined by my translational velocities, I use this 2-point theory, where for each point that I want to know the velocity of, I feed it another point on that same body that I know the velocity of, and I have to have the angular velocities of all of those bodies already defined. So the sequence that I did these things in here matters. I couldn't move the angular velocities down below this chunk on line 71 through 79 because then they're not known when I'm trying to use V2-point theory, and I had to do these definitions of the linear velocities in this sequence here so that I have these known velocities to feed in to these arguments here. Okay, let's define my new rigid bodies there. Just replacing A's with B's and C's here. And let's define my additional gravitational forces on those bodies. And let's define my joint moments. These get a little tricky sometimes. A tau here is the net moment acting on the trunk, and there's just one moment that acts on the trunk. It's that hip moment, tau 1. And so it just has this tau 1 here about the global z-axis, the axis coming out of the page, and applied to body A there. Okay. Similarly, for segment C, for the shank, it has a single moment, tau 2, and I'm going to arbitrarily give it a negative sign. And then for my other segment here, segment B, that one is a little bit more complicated. It was going to look like this. Okay, so you might wonder why exactly did I use these particular expressions here to define the moments here on A, B, and C, on bodies A, B, and C. Keep in mind here, the left-hand side of these expressions are not the moments at the joints. They're the net moments on those three rigid bodies, so the sum of all moments acting on them. For body A and body C, there's just one moment on acting on each of them. The hip moment acts on the trunk, and the knee moment acts on the shank. For body B, for the thigh, both of those moments, the hip and the knee moment, act on it, so it's got those, that's why both of them appear there for the thigh. Now, what about these positive and negative signs? Those are arbitrary. The reason I made this one positive and this one negative, there's no particular rhyme or reason to it. It just tells you what direction is positive and negative for that moment. For this body B here, though, notice that it has different signs on those same moments. And this is a Newton's third law deal here. The hip moment acts on both the trunk, segment A here, and the thigh, segment B here. And because of Newton's third law, the moment that is seen by those two segments that comprise that hip joint has to be equal in magnitude, tau 1, but opposite in direction. So one of these tau 1s needs a negative sign. So I gave the negative sign there on segment B. And similar story here for the knee moment, which acts on both the thigh, segment B, and the shank, segment C. That moment has to have equal magnitudes on those segments, but opposite directions because of Newton's third law. So one of them's got to be negative. And so that's why these certain joint moments appear in some of these expressions, but not in others, and why some of them have positive signs and some of them have negative signs for those joint moments. Okay, lastly, I need to define my new active forces, my foot ground contact forces. And we'll call that GRFX for ground reaction force in the x direction. And that's applied at 0.4, the ankle. And has a magnitude Fx1 in the global x direction. And then similarly a y component, Fy1 in the global y direction. Okay, after that it's just some bookkeeping. Add in my new kinematics to tell Keynes' method about. Add in my new kinetics. Add in my new rigid bodies. And we are ready to go. When I'm printing the equations of motion from Keynes' method to the screen here, this TrigSimp command is optional. It attempts to take these equations that you enter as the argument to TrigSimp here and attempts to trigonometrically simplify them so that they're shorter, more compact expressions, which is generally a good thing. For models that are more than a few degrees of freedom, like this 5-degree of freedom model here, or especially for a much larger model, TrigSimp here is generally not something that you want to use if you're printing the full equations of motion to the screen there. The equations quickly become very large, and TrigSimp will either take a really long time to run its simplifications, or will hang Python and it'll just never finish. So we're going to get rid of it here for now and see what we have here. And these are going to be big, so let's give it a little bit more room. And I'm going to run my 5-degree of freedom model. Let's see if we made any errors. Looks like I got lucky and did it right the first try. That doesn't happen often, but everyone gets lucky once in a while. Okay, so these are literally my equations of motion. This is F equals ma, or more accurately, F minus ma equals 0. When we're doing actual forward dynamics simulations with these equations, we don't want them in this form. Typically, we just want F by itself, and we just want m by itself, because we'll be using those to compute a, the accelerations, and then we use those accelerations to integrate numerically these equations forward in time to simulate motion of the model from some initial state. So with that in mind, we can get Python to, rather than printing our equations of motion, we can get it to just print the m part of F equals ma, and also just print the f part of F equals ma. Let's print some text to the screen here to label these things. And then we're going to have it tell us the mass matrix, which is the m part. And we're also going to have it tell us the forcing vector, which is the f part. And for these ones, we can usually use TrigSimp because they're smaller expressions, at least for this level of complexity. We can still get away with TrigSimp. Let's run that, see what we get. This will take a little bit longer, but should still run pretty fast. Okay, and so up here our mass matrix, that's the m part of f equals ma, and forcing vector, that's the f part of f equals ma. So I could divide the force by the mass, and I could get the acceleration vector there and use that to integrate my equations of motion forward in time. It's not obvious, probably just from looking at them right now. It won't be super clear until we actually take these and organize them into something that is more conducive to using in a program like MATLAB, which we'll do eventually. But this mass matrix up here, this is a 5 by 5 matrix of mass and inertia terms. And this forcing vector here, this is a 5 by 1 vector, one equation for each of the degrees of freedom in the model of the forces that are applied to the model. And so we're not quite ready to do musculoskeletal biomechanics simulations yet, because if you look at this forcing vector here, there's some terms in here we still need to define. For example, here you can see tau 1 and tau 2. Those are those moments at the joints, the hip and the knee, that we defined. Those joint moments are produced by muscle forces, and those muscle forces come from muscle models like the ones you guys made in homework number 1. So here we have our equations of motion of the skeletal system. Those are differential equations. And from homework 1, we also have the state equations, the differential equations for the Hill muscle model, for the activation dynamics and the contractile dynamics. So we need to take those equations and merge them with these equations to have a single combined set of differential equations that can fill these taus here, these joint moments, with the resulting kinetics of the actual forces that the muscles produce and actually produce those moments and move the model. So we still have to couple those together here. Similarly, we have fx1 here and fy1 somewhere else in this model, there it is, that are just symbolic right now, but we'll need to define them as a mechanical model of contact between that point and between the ground. And so we need to elaborate on that contact force a little bit and expand that into the actual mechanics of contact. Here it's just a nebulous symbolic force acting on the model. So that's where we'll be going next in class, defining contact between the feet and the ground, and defining these moments at the joints, including the effect of muscles and a few other things. And so that is where we're going in the near future in the class. So please take your 1 degree of freedom model, your code for your inverted pendulum, and repeat on your own what we did in class today. Take it and convert it from that 1 degree of freedom model into this 5 degree of freedom model. And I'll put both of these codes up here, the 1 degree of freedom version and the 5 degree of freedom version, up on the website to help you out with that if you get stuck on it. If you get stuck too, please feel free to email me if you can't get it to run. Okay, that is all for today. We will see you next time.